today we have Professor Clayton Shonkwiler here to talk to us. He is an assistant professor at Colorado State University. In 2002, he attended an ORU here at LSU, so we're all pretty happy to have him back here again. He was a visiting researcher at the Isaac Newton Institute and a recipient of the University of Georgia's 2014 Postdoctoral Research Award. He is a leading researcher in the study of random knots and random walks subject to topological constraints. But today, he's going to be talking to us all about 15 views of the hypersphere, something I'm pretty excited about. He also has an online art gallery for different depictions of mathematical things. There's just a bunch of still and GIF art, which I thought was pretty cool. I spent a good few hours just watching them all. So go ahead and view them at your own risk. But anyways, we also have a sign-in sheet being passed around, so go ahead and put your name and whether or not you're undergraduate, graduate, or professor. But without any further ado, let us all welcome the one and only Professor Clayton.
Well, thank you. That was quite the introduction. I didn't realize I was so infamous. So thank you, especially to the Student Colloquium Committee for inviting me. It's a real pleasure to be back. As you said, I was here in 2002, and it's great to be back. So 15 views of the hypersphere. That's sort of what I want to talk about. And so the hypersphere is just, everybody knows what the sphere is, right? And, so I'm thinking of a hollow sphere, so like a basketball, right? And that's a two-dimensional surface living in a three-dimensional space, and the hypersphere is, well, generalized one dimension up. So in 4 dimensions, you have this three-dimensional space called the three-sphere or the hypersphere. So hopefully, and basically, the moral of the story today is not any particular view of the hypersphere that I'm going to tell you, but more like when you're trying to visualize high-dimensional things, it's helpful to have lots of different ways of doing that, because every particular way of visualizing such a thing, if you don't have high-dimensional eyes, is a lie. And so it's good to have lots of different lies so you can see the commonality of the lies, and somewhere in there is the truth. So if you just have one lie, you're misleading yourself, but if you have 15 lies, you're doing a much better job, is my opinion. Okay, so the first way is, so visualizing was kind of a lie. Some of these things are not really visualizations at all. So the first way to think about the hypersphere is just purely algebraically. So you have what's called the zero sphere, which is just 2 points. So it's the set of points in the real line that are at a distance 1 from the origin, right? So that's 2 points. You also have the one sphere, better known as the circle, which is the set of points in the plane, which are at a distance 1 from the origin. So when the superscript on the R just means this is the line, this is the two-dimensional thing, which is the plane, this is three-dimensional space, and so on and so forth. So then the thing that we usually call the sphere is what I'm going to call the two-sphere, and it's the set of points in three-dimensional space that are at a distance 1 from the origin, right? So you can pretty easily guess where this is going to go. The next thing up is we're just going to take 4-dimensional space, whatever that is. We can certainly treat it purely algebraically. And we're just going to take the set of points where the sum of the squares of the coordinates is equal to 1. Okay, so that's a perfectly good definition, but like many definitions is completely useless as far as developing intuition. Okay. Now, this, you can also think not in terms of sort of real algebra. So up here, the x, y, z, and w are real numbers. But we can think instead in terms of complex algebra. So instead of talking about real numbers, we're going to talk about complex numbers. So first off, the complex numbers just look like real number plus real number times I, where I is the square root of -1. And we can visualize the complex numbers just as the plane, where you think of the real part of the complex number as the x-coordinate and the imaginary part of the complex number as the y-coordinate. And if you do that, then the circle is the set of complex numbers. Well, one way to think of this is the modulus is equal to 1. The other way is just if you take the complex number times its conjugate, you get 1. And of course, if you do this, if the complex number is x plus y times I, then ZZ bar is going to look like x squared plus y squared. So this is back, in fact, the original thing that we had, but thought about in a slightly different way. Okay. Well, now, so the plane is this two-dimensional space, which is like the complex numbers. The hypersphere lives in four-dimensional space, which we can think of as pairs of complex numbers. So now the three-sphere is going to be pairs of complex numbers z and w, so that when you take z bar plus w bar, you get 1. And again, if you write, z as x plus I times y and w as a plus b times I, this is just saying x squared plus y squared plus a squared plus b squared is equal to 1. So it's the same thing we had before, but thought of in a different way and in often a useful way. Okay. Now, there's yet another way to think about this algebraic. So I promise I'll get to the visualizations in a moment. But there's another very useful way to think algebraically about the hypersphere, and that's in terms of these numbers that are called quaternions. And so just as, well, so let me build up to that actually. So basically the slogan is that as complex numbers are to real numbers, quaternions are to complex numbers. So it's like a way to build up even further. So first off, the zero sphere is the set of real numbers whose modulus is equal to 1, or absolute value is equal to 1. This unit circle is a set of complex numbers whose modulus is equal to 1, as we just said a minute ago. Now it turns out that there's no good numbering system on three-dimensional space. So the reals are a one-dimensional number system. The complex numbers are a two-dimensional number system. This guy Hamilton in the 19th century spent many, many years trying to find a three-dimensional numbering system. He never could quite do it, but then he discovered that in fact, if you go to 4 dimensions, there is a natural number system, and it looks like this. You take numbers of this form, a plus bi plus cj plus dk, where now instead of just I being a square root of minus 1, all of these things are square roots of minus 1. And the slightly annoying thing is that the multiplication is non-commutative. If you take I times j, for example, you get k, but if you take j times I, you get minus k, which is kind of frustrating, but that's how it works. But then if you have a quaternion that looks like this, then you can take its conjugate just by taking minus signs where you had plus signs before. And then again, the three-sphere is a set of quaternions whose modulus, in the sense of taking quaternion times its conjugate and taking the square root, is equal to 1. So this is, again, this is the same as what we had before if you write, because what is this going to be under the square root? It's going to be a squared plus b squared plus c squared plus d squared. Okay. So that's a lot of algebra, and that's usually how these things are defined because the algebra is really easy to write down in textbooks, but maybe not so easy to understand. So now let's think about, okay, so the other slogan of this talk is if you want to think about four-dimensional objects as a three-dimensional being, you should think about what a two-dimensional being would have to do to visualize three-dimensional objects, and then do the analogous thing. Because you know what the three-dimensional object is, you have some sense of what the two-dimensional being would be able to perceive, and you can kind of extrapolate that relationship to the four-dimensional case where you actually don't know what the big picture is. So if we wanted to visualize the two-sphere as a being living in the plane, one way to think about it is, well, what would happen if you passed the sphere through the plane? What would you see as the being in the plane? What would you see? Yeah, so you'd see this, right? The first intersection would just be a point, and then the intersection would be these circles of latitude. They get bigger and bigger and bigger until you've got the equator, and then smaller and smaller and smaller again until you got to the other pole. Okay. So what would we see if someone passed a hypersphere through our three-dimensional space? Sorry, too many people said things at once. Okay, so that's exactly it, right? You would see one small, you would start at a point, and it'd get bigger and bigger and bigger until you got to the equator, quote unquote, whatever that means, and then smaller and smaller and smaller again until it disappeared. So the two-sphere was this sort of sequence of circles. The three-sphere is this sequence of two spheres. Okay. So, or another way to think about that, so I said seeing it as a movie, you're just treating the extra dimension as a time dimension, right? That's the same thing as what I said about passing the sphere through the plane or through the three space. Okay, another really fantastic way of visualizing the two-sphere if you are a being living in the plane is through this map called stereographic projection. So here's the actual map. You take a point on the two-sphere, x, y, z, and the output is this point on the plane, x over 1 minus z, y over 1 minus z. But the formula is not nearly so illuminating as the picture, which is now going off the screen. So let's see if I can. Okay, so what's the map? So I have a point on the sphere. I'm supposed to get out a point on the plane. What is that point on the plane? Well, I take my point on the sphere. I take the line connecting it to the north pole of the sphere. And then I see, okay, well, that line is guaranteed to intersect the plane somewhere. And the output is whatever that point of intersection is. And then you can see, like, if you move the point on the sphere to the south pole, then the point where the line intersects the plane is at the origin. And as you move the point on the sphere close to the north pole, the point on the plane is sort of going out to infinity in some direction. And so you can see, of course, that there's a problem actually at the north pole. There's not a unique line connecting the north pole to the north pole. So everything kind of breaks down at the north pole. But that's okay. You got everything except for one point. And so the slogan here is that the plane is the entire sphere minus that one point at the North Pole, which is often called the point at infinity. So you think of the sphere, so this is what people call the Riemann sphere, is you think of the plane, and then you think of the point at infinity as this extra point that you add on. And when you do that, the picture is something like this. So if you go backwards, take the inverse of that stereographic projection map. So now what I'm going to do is I'm going to take all these points in the plane, map them to the corresponding point on the sphere. And when you do that, you see that you're sort of wrapping the plane around the sphere, and everything's sort of going nicely until something really crazy happens at the North Pole, right? Because somehow, no matter which direction you go out to infinity, you have to end up at the same place in the end. So somehow you're taking this entire plane and you're sort of smushing everything at the North Pole, sort of at the last instant. Okay, so that's what I want to say. So first off, let me just do a slight digression because I really like this picture. So what I'm going to do is I'm going to take the usual cube in three-dimensional space, and I project it onto the sphere, the inscribed sphere. So every point on the cube, you just take the line connecting it to the origin. That gives you some corresponding point on the sphere. And so now you get this sort of, curvy-looking cube sitting on the sphere. I'm really just looking at the edges. And then if you map that down to the plane by stereographic projection, well, now each of these red points you're connecting to the North Pole, and you're looking where that line intersects the plane, and you're recording that point as some red point on the plane, and you get this sort of flower-looking thing. And so this is like if you're a two-dimensional being, and you're trying to visualize the three-dimensional cube, this would be a way of doing it, this weird sort of flower shape. And then you might ask yourself, okay, well, what happens if we move the cube up in three space around? What does the two-dimensional being see? And of course, if you rotate around the z-axis, you're just rotating this flower picture along with it, right? So that's not so exciting. Rotations look like rotations when the rotation is around the z-axis. But now if you rotate around a different axis, things get much crazier. So now I'm going to rotate around the x-axis. And you can see the flower in the plane. It doesn't look like it's rotating at all. It's doing something really weird. And so if you were just this planar being and had no conception of three-dimensional space, here's what you would see. I sort of like this as a right? That's a rotation. A three-dimensional rotation seen from two-dimensional eyes. Okay. So, yeah, right. Now, you can do exactly the same thing for the hypersphere. You say, okay, I have this, this sphere in four-dimensional space. I can take any point on the sphere except the point 0, 0, 0, 1, take the line connecting that point to the point 0, 0, 0, 1, find out where it intersects the plane where, w equals 0, so just the x, y, z space. This is the map sort of purely in terms of coordinates, but it's geometrically it's exactly the same thing. And so the end result is that three-dimensional space, all of it, is like the hypersphere minus the one point at infinity. Or in other words, if you want to build the three-sphere, you take three-dimensional space, add a point at infinity, and everything sort of mushes up in some crazy way at infinity, just like in the picture that I had before. And so now what you can do is you can take the hypercube and do the same thing that I did with the cube, project it onto the three-sphere, stereographically project down to three-dimensional space, and here's what you get if you do that. Okay, so now if I rotate around sort of the w-axis, it looks like a nice, rotation. So this is a four-dimensional rotation that actually looks like a three-dimensional rotation after this stereographic projection business. But if I take a four-dimensional rotation, where I rotate in the xw plane, so including one of my xyz coordinates, then it looks like this. Which I think you'll agree doesn't really look like a rotation, but actually is. Or here's the same thing from a slightly different vantage point. I don't know, I just like that. So that's a rotation in four space viewed with our three-dimensional eyes. Okay.
What axis are we looking at?
Well, you're not rotating around an axis, right? Because the rotation is in the xw plane, and then I'm projecting from the the 0, 0, 0, 1 point, the stereographic projection. So yeah. The perspective is from the point 1, 1, 1, I believe. It's one of the corners of the three-dimensional cube. Yeah, yeah. Okay. So stereographic projection is a really powerful tool for visualizing the three-sphere. You just say, well, you already know how to visualize three-space, and that's what it is, except for this one crazy point at infinity. Okay. Here's a way of thinking about things that turns out to be equivalent, but seems very different, if I can get it to show up. So here I claim is a picture of the usual two-sphere as visualized, in a particular way that a two-dimensional being could actually understand. So how is this a picture of the two-sphere? You're not allowed to answer. Neither are you.
Seems just like almost topography kind of graph, the darker color corresponds to being higher.
Yeah, exactly. So the color is actually telling you the z-coordinate, if you like. So let's see which way I did it. I've now forgotten. So here's how it really is. I slide these two guys on top of each other, glue their boundaries together, and then blow it up like a balloon. So more red means more positive z-coordinate, down to white, I promise you it's actually white right in the middle, is 0 z-coordinate, and then blue is like negative z-coordinate. And so another way to think about this is think of this as like, the color scheme is because I think about it kind of as temperatures, like it's hot here, it's cold here, and the temperatures match on the boundaries. And so if you were a two-dimensional being, you would one way to think about, okay, you're supposed to take this disk, which I understand really well, and this disk, which I understand really well, and I'm supposed to glue their boundaries together in some way. And so of course you can think like, okay, well, if I'm, I'm moving in some path on this theoretical two-sphere, which I don't really understand, okay, you move out here, well, this point's the same as that point, so then I'm coming in here, and you move around, you come out here, and then you're coming in here, and so on and so forth. You can track like what motion looks like in this space perfectly fine, even though you can't really visualize the thing upstairs. Another way to think about it, although this is, I guess, the reverse of the gluing that I showed, but you can think about, okay, well, we're gluing this point to this point, and 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 so on and so forth. Like, let's say the blue one is sort of enveloping the red one. Sort of you're gluing as you go along the way. But then something really crazy happens, because this point has to be glued to this point. But you're sort of coming from these different directions, and this point's going to here, and this point's going to here, and so as this amoeba is sort of eating over the thing, like something really weird has to happen at that last instant. And so again, that's like in the stereographic projection thing, like you have this weird thing happening at infinity, and that's sort of the same phenomenon there. So here, of course, is the corresponding picture of the three-sphere, which doesn't quite fit on the screen, but hopefully you get the idea. This is now a solid ball, colored, darkest red right in the middle and getting lighter and lighter and lighter as you come out. And this is a solid ball, and it's blue in the middle and lighter as you come out. And then again, you're just supposed to glue the boundaries together, like slide the one over the other, glue the boundaries together, and then inflate in some four-dimensional way that's really hard to picture, but that's what you're doing. And again, you can think of sort of the amoeba eating this guy and then something kind of crazy happening at that last moment, which sort of requires the fourth dimension to really happen. Let me just say that if you read Dante's Inferno, this is, in my opinion, the shape of his universe, like the Divine Comedy, rather. So the Inferno, like you go inward until like the ninth circle of hell is in the very, very middle, right? And then when you get to Paradiso, he starts sort of at the outside, and God is like right in the middle of these sort of concentric spheres of angels and archangels and et cetera, right? So you have this sort of sphere with concentric smaller spheres with the devil at the middle, and these spheres with concentric spheres with God at the middle, and like how do you glue them together other than in this exact way of building up the three-sphere? My theology is probably way off, but this is my opinion of what's going on. Okay, so fine. That's one way of thinking about it. Here's another way of thinking about the three-sphere, again, by sort of building on analogies with the two-sphere. So topologists have this operation they call taking the suspension of a space. So what does it mean to take the suspension of a space? You have your space, you add 2 points sort of wherever you want, and then you connect both of those 2 points to every point in the space. In principle by line segments, but by whatever curve happens to be convenient, probably. And so I claim the two-sphere is the suspension of the one sphere, otherwise known as the circle. So here's the picture. Here's the circle. I add 2 points, and then I'm supposed to connect these 2 points to every point on the blue circle. So, and more generally, when you're taking a suspension, you have your space, which you think of as blue, you have your 2 points, which you think of as red, and you connect red to blue in every possible way. So when you do that, of course, so here I connected the red to a bunch of points on the blue, but of course, really there's infinitely many of these lines, so it doesn't really look like a collection of lines, it really looks like this. And if you're a topologist, you don't care so much about corners, so you just round off the corners, and you get the two-sphere. Don't say anything. Yeah. We're going to pretend you don't care about corners if you're a topologist. It's not really true, but all right. So that's how you see the two-sphere as a suspension of a circle. Now notice that this picture that I started with was really a three-dimensional picture. So the question is, how would you make this picture if you were a two-dimensional being? Well, I claim it would look something like this. The smart way to do it is to put one of the circles, or one of the points that you add inside of the circle. If you don't, you're asking for trouble, basically. So here first I'm going to do it sort of in stages. So first I connect that red point to all the blue points. So that gives me this collection of lines, but really that's just a solid disk. So I have this purple disk. And then the challenge is, okay, now I'm supposed to connect every point on the blue circle to this point, this red point. And you're not allowed to have the curves connecting this point to this point and this point to this point intersect. They're all supposed to stay, away from each other. So you can't really do it with straight lines, but you can do it with something like this. So here I'm connecting this point to all of the blue points using these curves. And of course, really you have to imagine that there's, this entire space is filled in with purple, right? And again, something weird is happening, right? Because there's this line that's shooting straight out that way and coming in straight in this way and connecting this point to this point by going sort of off to infinity and around the corner. So there's something a little bit weird going on, but that's the best you can do in terms of visualizing this suspension from purely two-dimensional eyes. Okay, and so if you want to build the three-sphere, it's the suspension of the two-sphere. And the way to do it is, okay, you have your blue two-sphere. You add these two red points, and then you're supposed to connect the red points to all the blue points. And whatever you end up with is supposed to be the three-sphere. So it's just like the picture we just had. First, you connect the inside one, to all of these points. And so all that you're doing then is you're filling in that ball and making it a solid purple ball, like that. And now you're supposed to connect every point on the surface of this solid purple ball to this point. And again, it's really hard to visualize without having four-dimensional eyes, but it's something like this. And again, well, I actually failed to do it properly, but there's something that's going straight out this way and coming in straight in this way. Okay, so in fact, this is secretly the same picture as before. This is like, you have this solid ball and the solid ball around this point, and this solid ball is, amoebaing over and enveloping this one till it's kind of inside out. So it's actually the same picture as I had before, but viewed in a different way. So your two red points end up being the centers of those two solid balls. Okay, good? I should have said at the beginning, if you get lost, that's okay. Each of these is sort of more or less independent, so don't worry about it too much. All right. Here's another picture of the two-sphere. How does that work? Yeah, exactly, right? So it looks more obvious if you do that, right? So I had those two disks and that annulus, and I glue them together in the way that's sort of obviously prescribed by this picture, and you're guaranteed to get back the two-sphere. But again, this was the actual picture that you saw as your two-dimensional being, right? Okay. So now I claim that the corresponding picture of the three-sphere, well, can anybody guess what it is? I'm going to be gluing some stuff together. Okay, so yeah, that's the picture I have. So I claim that this is a picture of the hypersphere. And so the idea is that this is a solid torus. This is a solid torus, so just like a solid donut, right? And then somehow you're supposed to glue the boundary of this solid torus to the boundary of this solid torus. And if you do it in just the right way, you're going to get back the hypersphere. And this is a little bit harder to picture because something weird's going on with the hole in the middle, right? So the better way to visualize this is if you draw the picture like this. And now it's kind of clear how the gluing is supposed to work, right? You glue this point to that point, and this point to this point, and this point to this point, and this point here to some point over here, and this point over here to this point here. And you kind of wrap the red around the blue in some way. Again, something kind of crazy is happening with this point being glued to this point. The maybe even better way of visualizing this is to think about the red torus like this. Right? Instead of, because this is more symmetric, right? And so now there's just something crazy that this solid torus has some weird point at infinity happening. But But it's clear how to glue everything, right? This to this and this to this and so on and so forth. And in fact, if you draw the picture a little bit bigger, what's really happening is this. But now the red torus is inside out. Like the inside of this solid red torus is out where we are. And the outside of the solid red torus is inside where the blue thing is. And then you just glue the boundary of the red to the boundary of the blue, and you get the three-sphere. Okay. So this is an example of something that's called a Haggar splitting. Well, so is the solid ball picture. But so in general, what we just did was we said, okay, well, we glued the blue to the red in such a way that it came together to become the three-sphere. And so you can actually record that with this picture right here that, oh, okay, there we go. So what did I do, right? I had my blue torus, and then I glued the red torus to it in such a way that this circle, this green circle here, was glued to this green circle here, and everything was sort of wrapped around from there. So let me just, again, this was the picture, right? If you do it in that more symmetric way, this green circle on the red is glued to this green circle on the blue, and everything else kind of gets wrapped around. And so it turns out that those two green circles tell you all the information that you need about how to build this space. So what you can actually do is you can just record. So this is in fact a picture of the three-sphere. So this is not a solid torus, this is a hollow torus, and it has two curves on it, a blue curve and a red curve. And what this is telling you is, well, secretly you had the blue solid torus and the red solid torus, and you glue the boundary of the red solid torus to the boundary of the blue solid torus by gluing this circle on the red to this circle on the blue, and then wrapping everything around. So this is an example of what's called a Haggar diagram, and it turns out that Haggar diagrams are really, really useful ways of visualizing these three-dimensional manifolds that sit in four-dimensional space or higher dimensional spaces or whatever. So you sort of abstracted away some of the picture, but now you have a surface with some curves on it, and that tells you like lots and lots and lots of things about the space that you're actually looking at that's really hard to visualize. Now, of course, there's many, many different surfaces, not just the torus, right? And so it turns out that there's many, many different ways to visualize the hypersphere. Here's another one. Why are you not? Okay. I don't quite know what's going on there, but okay, hopefully you can sort of see what's going on, right? Now I have this three-hole donut, and I have these three blue curves and these three red curves. And again, the idea is that, well, you really have two solid three-hole donuts and you glue them together in such a way that's encoded by these six curves. And here's another picture that I was too lazy to make in Mathematica, so I just drew it by hand. But now I have this two-hole donut, and I have these two red curves and these two blue curves. And the two blue curves, if you notice, don't intersect. So I have one that starts here and goes around and wraps around and comes around the back and then meets up. And then this other one that does this thing. And this is also, in fact, a picture of the hypersphere. But, for example, this is not a picture of the hypersphere. And so it turns out there's an entire calculus of like moves that you're allowed to do to transform your hypersphere or whatever your space is, just in terms of manipulating these blue and these red curves, which is a really, really powerful tool.
Could you briefly go back to the previous?
Yeah. Okay. So, all right. So this is powerful stuff. Okay. So here's yet another way. So topologists have another operation. Suspension wasn't enough. There's also an operation called the join. And so now here's the idea. You have a blue space and you have a red space, and you connect every point in the blue space to every point in the red space by some curve. So before we just had, a blue space and two red points. Now it's a blue space and an entire red space. But otherwise, it's basically the same idea. And so, for example, if we want to build the circle, we can take it as the join of a zero sphere and a zero sphere. So I take two blue points, two red points, and I connect every red point to every blue point. And what do I get? Well, I get something like this, right? And if I round off the corners, so instead of making these line segments, I make these quarter circles, I get the whole circle. So this is the one sphere as the join of two zero spheres. Now we've already seen this next picture. The two sphere as the join of the one sphere and the zero sphere. So I have my blue space, I have my red space, I connect every point in the red to every point in the blue, and you've already seen this, so you get that, right? Okay, so we saw the one sphere was the join of two zero spheres. The two sphere was the join of a one sphere and a zero sphere. So what is the three sphere? So two one spheres, right? In fact, we already saw, it's also the zero sphere and the two sphere, which we saw before. That was the suspension picture, right? But we can also do it as the join of two one spheres. So here's that picture. So I have a blue space and a red space, these two circles. It turns out to be very convenient to link those two circles, just like the tori bit that we had before were linked. And now I'm going to take every point in the red and connect it to each point in the blue. So for example, if I connect every point in the red to that blue point, well, I get a bunch of lines that really fill out a solid disk, right? And then I say, okay, well now go around, connecting every point in the red to the next point in the blue and so on and so forth, and you get a giant horrible mess. Okay, well the moral of the story, of course, is that like you shouldn't use straight lines. You should use circle arcs. And so here's how you do that. So now I take every point in the red, I connect it up to this point in the blue by this collection of circle arcs, and you're filling out a solid disk. But now as I move around, I do it like this. So what's happening here is at each stage, I'm connecting every point in the red to the point in the blue by a collection of circle arcs that fill out part of a round two sphere. Except something kind of weird happens. Again, this shouldn't be surprising here, right? Where I'm connecting this to this sort of point over here, because now I have, I'm circle arcs that are filling out this two sphere of infinite radius, which is really just a plane. And again, something weird's happening. This point has to be connected up to this point, sort of going out, through infinity. So that's a picture of the three sphere as a join of these two circles. Now, if you draw the two circles in a slightly different way, so if I think of the red circle as being a circle that passes through the point at infinity, then it's a circle of infinite radius, which is otherwise known as a straight line. And now I connect every point on this red line to every point on the blue by a collection of circle arcs. And if you do it in just the right way, you get a collection of planes that fill out as you go around all of three space. So every point in three space lies in exactly one of these vertical planes, half planes. And of course, again, you have this one extra point at infinity, which is kind of weird. So this construction is called an open book. And the reason it's called an open book is because if you draw all the planes together, it looks like you did something the librarians tell you never to do, which is to take your library book and smush the two covers together and have the pages splayed out, right? So these planes, or in general the surfaces that you get, are called the pages of the open book. And this is, again, a really powerful way of visualizing these higher dimensional spaces, is in terms of these open books. Okay. So here's another really cool construction on the hypersphere. So now again, I take this blue circle and this red circle, where the red circle sort of goes through the point of infinity. The other way to think about this is the unit circle in the xy plane This is the unit circle in the ZW plane, and I'm just visualizing it by doing the stereographic projection. So really this is supposed to be a picture up in the hypersphere, but I visualized by stereographic projecting down to 3 space where I know, how to use my eyes. And so now if you take the collection of points that are exactly halfway in between the blue and the red, you get a torus, which is called the Clifford Torus. And then something you can do on the Clifford Torus is you can foliate it by curves that look like this. So each of these curves, doesn't intersect any of the other curves, and every point on the torus lies on exactly one of these curves. And then what happens is, well, if you think about, okay, the points that are, a distance r away from the blue, well, that's some smaller torus. And, so you interpolate between these two circles by this collection of tori, one of which is this torus that's halfway in the middle. And if you take this foliation along for the ride, you get a picture like this. So starting at the blue, and then you get a collection of circles that come out, come out, come out. And then the torus is getting bigger and bigger and bigger, and then you collapse down on the other end. Okay. So this picture is also closely related to the complex algebra that I talked about before, but I don't really have time to describe it. Let me just say that one really amazing fact is that if you take all these circles together, they all link each other exactly once. So you can sort of see in this picture, well, the circle that was in the middle links with this one exactly once, and all of these guys are linked with each other and with all the other ones exactly once. And if you fill out the entire space, maybe I won't go all the way, but you get this crazy collection of circles all linked with every other one in exactly sort of one thing. Okay. So here's another way to think about the 3-sphere. So now imagine that you're a two-dimensional being living on the surface of the 2-sphere. It shouldn't be so hard because you kind of are, right? One dimension is really small, so it's almost two-dimensional. And so now you imagine that you're living at the North Pole. You're a two-dimensional being. You have two-dimensional eyes. All you're aware of is sort of 2 dimensions. And of course, the space is this curved space, and so like your light travels along the surface of the sphere. So this is how it's not like what we are, right? So light is going to travel along the surface of the sphere. So when you look out, these red things are your lines of sight. And then if now I have this red disk sitting on top of you, and so everywhere you look, you see red, because the red is like, everywhere you look, you see red, so all of your lines of sight are red. And now what I'm going to do is I'm going to move that red disk off of you a little bit. And then you see that, when I look in this direction, I see the red disk, and so those lines of sight are red. When I look in this direction, I don't see the red disk, so I'm just going to color those blue, just so that it's very clear that you're not seeing red, right? But something weird happens, right? If you look towards the red disk, of course you see red, but if you look away from the red disk, you also see red. Because this line of sight goes around the back and passes through the South Pole and comes up and hits the red over here. So if you're living on the 2-sphere and you have this red disk, well, if you look towards it, quote unquote, you see it. But if you look away from it, you see it sort of going around the back. Okay, so that's weird. Here's another thing that's weird. As the red disk moves away from you, of course, fewer and fewer lines of sight intersect it. So it appears to be getting smaller and smaller and smaller, as you would expect, right? It's moving away from you, it's getting smaller. Okay, but something weird happens. It gets far enough away from you, eventually, that more and more lines of sight start intersecting it again. And so what does that mean visually? It means it's looking bigger and bigger and bigger, even though it's still moving away from you. And then as it comes to the antipodal point, right, it's as far away from you as it can possibly be, but every direction you look, you see it. So geometrically, like living in the 2-sphere is really different than living in the plane. And the same is true if you lived in 3-space. So now, instead of a red disk, I have the Earth. And the Earth is right now sitting on top of me, so I see it sort of everywhere. But now as it moves away, it gets smaller and smaller and smaller and smaller and smaller, just as you would expect. Okay, but now it's still moving away from me, but it's getting bigger and bigger and bigger and bigger again as it gets to the South Pole. And then notice as it passed, it's hard to see, but as it passed through the South Pole, it now looks sort of upside down because I'm looking, the other way around. And now it's moved past the North Pole. It's now coming up from behind me, and I'm seeing it sort of going all the way around, and it gets bigger and bigger and bigger, and it passes from behind me and then passes over and through me. So this is what it's like to live on the three-sphere. Things don't necessarily get smaller as they move away from you. And you have eyes in the back of your head. And so, for example, if nobody's standing at the antipodal point, you can see yourself, right, going all the way around. You can see your backside. So it turns out, and you have that special point where someone could stand at the other point and you see them in every possible direction. And that's true of every point on the sphere. Everybody has sort of their anti-friend, point at the other side. And so it turns out that the sphere is the only three-manifold with the round three-sphere is the only three-manifold with this property. This is what's known as the Blaschke conjecture, and it was a major, problem that was solved in the 20th century. Okay, so I'm coming towards the end, so let me finish with another famous conjecture that was proved not so long ago, called the Poincare conjecture. So this says if you take the two-sphere, well, this is not what it says, but if you take the two-sphere and you take any weird, crazy curve you like on the two-sphere, you can always smush it to a point without breaking it. So this maybe this curve isn't so crazy, but you can see you can just smush that curve to a point in a fairly straightforward way. But the two-sphere is sort of the only surface that doesn't have boundary that has that property. So for example, if you take this weird blue curve on the torus and you try to smush it, well, you can smush it to a nice round circle, that's fine, but you can't go any further without breaking anything, right? You can't jump the gap without breaking your donut, without crossing the hole. Or likewise, if I take this crazy curve, I can certainly smush it to a nice round circle, but I can't sort of jump the gap, right? And here's a picture. If you're a two-dimensional being, how do you visualize that torus? Well, you visualize it like this. You take a square, you glue these two sides together to form a cylinder, and then you glue these two sides together to form a torus. And then that curve that I had before is like this crazy curve here, and then so you see that you can flatten it out to a nice straight line. But remember, this is glued to this, so this is really a circle, but you can't do any better than that. So if you're talking about the hypersphere, well, the hypersphere, remember, it's like R3 plus an extra point. And so if you have a curve, you can just smush it to a nice round circle and then squash that down to a point, no problem. And the Poincare conjecture says this is the only compact three-manifold with this property. So here's an example of a different three-manifold that doesn't have this property. So just like before, to get the torus, I took the square and glued the sides together to get this torus. I can take the cube and glue the left and the right and the front and the back and the top and the bottom together, again in a way that's really kind of hard to visualize with three-dimensional eyes. And then this curve is actually a loop, right? This point is glued to this point. This is a loop, and I can do this business of straightening it out, but I can't contract it down to a point. That's the best I can do. Okay. Let me just end by saying that one of the really useful things about quaternions, so one of the ways to think about the circle is the collection of rotations of the plane. So if I take this red shape in the plane and I rotate it, I can specify the rotation by specifying an angle. What's an angle? An angle is a point on the circle. And so as I rotate this guy around, I'm just specifying the rotation by the point on the circle. Now it turns out you can specify a rotation in three space. Well, one way to do it is by specifying an axis and then specifying an angle about what, where you rotate around that axis, how much you rotate around that axis. And if you choose a different axis, you can rotate around that axis, and you choose a different axis, and you rotate around that axis. So a rotation of 3 space is determined by an axis and an angle to rotate around that axis. And using a particular formula that looks like this, you can turn any rotation into a, well, not quite unique, but more or less unique quaternion. And of course, the 3 spheres, the unit quaternions. And so if you do this rotation, you can look at the corresponding points on the 3 sphere, which are these 2 guys. And as you move around, they move around. Okay. So that connects. This was a little bit fast, but the point is the quaternions are really, really useful for things like computer graphics, because they're a really nice way to encode rotations in a computationally nice way. Okay, so that's it.
All right, so at this time, we'll open the floor to any questions. Going once.
Yeah.
What about the thing they call octons?
Octonians? Yep. Okay, so the octonians, yeah, so that's a numbering system. Otherwise known as Cayley numbers. So this is a numbering system on 8-dimensional space. So instead of quaternions, there were 4 things, 1, I, J, and K. Now you have 8 things. You still have 1, and now you have 7 of these like imaginary units, they're called. And then if you take the unit octonians, this corresponds to the 7-dimensional sphere, so the unit sphere in 8-dimensional space. And so this gives, in particular, this tells you that this has some really nice properties that so the 1 sphere, the 3 sphere, and the 7 sphere have really nice properties that others don't, because they correspond to the the complex numbers, the quaternionic numbers, and the octonionic numbers. But it turns out in general that these are basically it as far as high-dimensional numbering systems go. So this is sort of the last. Well, I mean, I'll say any more about that, but those do give you a really nice way of visualizing the 7 sphere in very analogous ways, like the Hopf fibration generalizes to the circumstance, and various other things that I talk about also generalize because of this connection to the octonians.
We did the thing with you're talking about the sphere kind of being wrapped around the other sphere. And then we also did something similar with the torus. And that seems weird to me because the torus has genus 1 and the sphere doesn't. So, but you're still wrapping them around in a similar manner, so you're not getting a problem with the holes. So that just seemed confusing to me.
Yeah, so basically the idea is like you can take a surface of any genus. So this is a surface with no holes, so this has genus 0. This is a surface with 1 hole, that has genus 1. You could also take the 2-hole torus or the 3-hole torus, or et cetera, et cetera, et cetera. And there's sort of so I showed you, well, if you glue this circle on one to that circle on the other, you get the 3 sphere. And if you glue these 2 circles on this one to these 2 circles on that one, you get the 3 sphere. And so it turns out that in general, you can always, whatever your Haggar diagram is, I'm just going to draw a stupid one. You can always attach on a piece that looks like this by what's called a connect sum operation. And so you just add on one of these more or less trivial kinds of things, and you're guaranteed to get the same thing you started with. So when I glue this onto this, I'm guaranteed to get the same thing I started with, which was the 3 sphere. And when I glue this onto itself, I get this, so that's guaranteed to be the 3 sphere. And when I glue this onto this, I get this, which is guaranteed to be the 3 sphere, and so on. So this operation is called stabilization, and it's a way of sort of changing your Haggar diagram without really changing anything about the space that it's referring to.
Is there some kind of group structure on something? I mean, so that's an identity element.
Inverses is tricky. Yeah, I don't know. Shay, is there a group upper? No, I don't think so. It's it's like a monoid. Connect sum is like a monoid. And so you get kind of a. Yeah, I don't think so, but yeah. So there is a theorem that says two of these pictures are of the same space upstairs if they're related by a sequence of moves. Like, I mean, there's this move and there's a couple of other moves that I don't want to get into. But there's sort of an if and only if thing. Like, you know, there is such a picture for every possible three manifold, and two pictures are the same if they're related by this finite list of possible moves. Yeah.
Well, if there are no other questions, let's thank our speaker one last time.